this is lecture 2 of elementary number theory. So today we will start from congruences. So first we will discuss what is congruence modulo m. Okay. So what is congruence modulo m? So first we will discuss the definition, or before going to the definition, we write sometimes that 5 divides 23 minus 3, or say 20. So 5 divides 20, or 5 divides 23 minus 3. So we write here 23 congruence 3 modulo 5. Okay. So the definition of modulo is, let A is an integer. So A is an integer. So if we write A is congruent to integer B modulo m, means we write A congruent to B modulo m, and it means m divides A minus B. Okay. So if m does not divide A minus B, then m is not congruent to B modulo m. Okay. So we know that if m divides A minus B, so it means the remainder, when we divide A minus B by m, so we get 0 as the remainder. So we can also write A minus B congruent to 0 modulo m. So they are same. They are the same. A minus B congruent to 0 modulo m, or A congruent to B modulo m. Okay. So there is a result related to the congruence. So result states that A congruent to B modulo m if and only if A is equal to B plus K m for some integer Okay, and where a, b and m are integers as well. Okay, let's see the proof of this result. Okay, so suppose, because this theorem is with if and only if, so we consider that first part of the theorem is true, and then we will prove that the second part must be true, and then vice versa. So we suppose A is congruent to B modulo M. So we just apply the definition of congruence modulo M. So this definition says M divides A minus B. So if M divides A minus B, so A minus B must be equal to some integers time M. For some integers, for some integer M. For example, if we say 6 divides 24, so we write 24 is equal to some integers time 6. So the integer is 4 here. So similarly, if M divides A minus B, it means A minus B must be equal to an integer times M. Then we can take negative b to the right hand side, or we add b both the sides in this equation, we get A is equal to B plus Km. That's the required result. Okay, so now we have to prove the converse of the theorem as well. So conversely, assume that A equals B plus Km. So this part is also very easy. For some integer K. Okay. Then, so if A is equal to B plus Km, then we can write A minus B equals Km. Okay. So if A minus B is equal to Km, so it means both K or M divides A minus B. So we can write M divides A minus B. So we can apply the definition of congruence. So it means A is congruent to B modulo M. That's it. Now we have the second result. Second result gives some additional properties related to congruence. So the result states that congruence means this sign is an equivalence relation. Okay, so it means So, it has three properties: reflexive, symmetric and transitive. Okay. So, first is reflexive property, means A congruent to A modulo M. This is called reflexive property. Okay. The next one is symmetric property. So, we say if A is congruent to B modulo, then B is congruent to A modulo M, and this is called symmetric property. Okay. The third one is if A is congruent to B modulo M and B is congruent to C modulo M, then A is congruent to C modulo M. And this property is called transitive property. So, it means we have transitive property. So, it means here we have to prove these three properties. If we are able to prove three properties, it means congruence is an equivalence relation. Okay. So, for the first, we know that M always divides 0. Okay. This is for the first one. So, if we make numbering here, this should be proof. Numbering 1, 2, 3. So, for 1, M always divides 0. This implies this 0 could be replaced by A minus A, and here we can apply the definition of congruence. So, if M divides A minus A, then A is congruent to A modulo M, and this proves reflexive property. The second one is the symmetric property. So, if we have A congruent to B modulo M, then B congruent to A modulo M. Okay. So, if A is congruent to B modulo M, so here we will invoke the definition of congruence that says M divides A minus B. So, A minus B is an integer and M divides that integer. So, M will also divide the negative of that integer, then M then M divides B minus A also. Now, we apply the definition of congruence, which states B is congruent to A modulo M, which proves that if A congruent to B modulo M, then we have B congruent to A modulo M. Third one is the transitive property. So, for transitive property, if we have A is congruent to B modulo M, B modulo M, which means M divides A minus B, and we also have B congruent to C modulo M, which implies M divides B minus C. Okay. So, M divides A minus B and B minus C. Okay. So, if A minus B and B minus C are both divisible by M, then their sum must be divisible by M. Okay. So, we can write hence M divides A minus B plus B minus C. So, which gives you minus B plus B cancel, which gives you M divides A minus C. And if we convert that into the congruence, which gives you A congruent to C modulo M. That's it. Okay, let's move to the next result. So, we have another result, A congruent to B modulo M if and only if A and B leave the same remainder when divided by M. Okay, so that's the statement. So, the remainder, so it means this result is with if and only if condition. It means you can use this result in both way. So, A congruent to B modulo M if and only if A and B leave the same remainder when divided by M. So, remainder will be same whether you divide, okay, whenever you divide that expression by M. Okay. So, in both cases. So, because this is if and only if condition, so we will start our proof. Okay. So, we suppose A is congruent to B modulo M. Okay. So, we suppose that this congruence is true, and we have to show that the remainder when a and b are divided by m, so then there will be the same remainder. Okay. So, by first theorem that we studied earlier in this lecture. So, if A is congruent to B modulo m, then A is equal to B plus K m for some integer k. Okay. And now we apply division algorithm here. So, by division algorithm, if B is divided by m, if this B is divided by m, then we suppose that n r is the remainder, okay, which should be greater than or equal to 0 and less than m. So, in that case we write B is equal to m q plus r, where r is greater than equal to 0 and less than m. Okay. So, according to division algorithm, if B is divided by m, so then there must be unique integers q and r such that B is equal to m q plus r and r is greater than or equal to 0 and less than r. Then we substitute the value of B in equation. For example, this is equation 1, we put that value in equation 1. So, 1 implies A equals m q plus r, and we have already assumed that whenever B is divided by m, the remainder is r, and now we are showing that whenever A is divided by m, then the remainder A will remain r. Okay. So, we replace B by m q plus r, okay. Then we have k m. So, we write k m here. So, now this can be written as m q plus k m plus r, and if we take m as common from here, so we write q plus k plus r. So, if we use division algorithm, and according to division algorithm, if A is divided by m, then we have some unique integers, so such that A can be written as m times some integers plus r. Okay. So, in the case of B, we assume that B is divided by, in the case of B, we assume that B is divided by m. So, we have integers, unique integers q and r, such that B can be written as m q plus r, where r is the remainder that has values greater than equal to 0 and less than m. And now we are proving that when A is divided by m, then there will be same remainder r. Okay. So, if we use division algorithm, so look at here in the first term and in the last term. So, here m is divided by A is divided by m. So, A is divided by m. So, we have unique integers q plus k and r, such that A can be written as m times q plus r plus q plus k plus r, okay, where r is greater than equal to 0 and less than m. So, that proves the first part of the result. Now, we have to show the converse of that. So, conversely, assume that both A and B leave the same remainder when divided by okay. And now we have to show that A congruent to B modulo M. Then we apply division algorithm here, because then by division algorithm A, whenever A is divided by M, we have remainder R. So, according to division algorithm, there must be two unique integers Q and R such that A can be written as M Q plus R. We can call this equation as equation 1. Similarly, if B is divided by M, then by division algorithm there must be two unique integers, suppose q prime and r. Okay, we have to take the same r because it is given here, the remainder is same. So, m q prime plus r, we call this equation as 2. And where the value of r is greater than equal to 0 and less than m. So, if we subtract equation 2 from 1, so subtract equation 2 from 1, we get A minus B equals m q minus m q prime and r cancelled. So, A minus B equals to m times q minus q prime. So, both q and q prime are integers. So, it means difference A minus B is equal to m times q minus q prime. We can replace this q minus q prime with an integer, for example k, and we take minus b to the right hand side. That becomes A equals b plus m k. And now, by our first result, this can be written as A is congruent to B modulo m. That is the complete proof of our result. Okay, let us do an example. that's the application of the first part or first result as well. So there is an example. So no prime of the form for n plus 3 can be expressed as the sum of two squares. Okay. So no prime of the form 4n plus 3 can be expressed as the sum of two squares. Okay. So we will solve this example, or we will prove this result by contradiction. So we assume that let n be the prime of the form 4n plus 3. Okay. Or means we can write n is equal to 4n plus 3 or 3 plus 4n. Okay. So by using the congruence, we can convert this. For example, this is a, this is b, and 4 is m, and this is an integer k, for example. So we can convert this into a congruence. N is congruent to 3 modulo 4. Okay. So if n is a prime, so any number which is of the form 4n plus 3 can be written as 3 modulo 4. Okay. And here we have to show that there will be no prime, or there is no prime of the form 4n plus 3 which can be expressed as a sum of two square. And we have taken that we have already taken n is a prime of the form 4n plus 3. So to show this thing by contradiction, we assume n is equal to the sum of two squares, where a and b are two integers, for some integers a and b. Okay. And now 4n plus 3 is odd. Okay. So it means n is an odd prime. Okay. So if n is an odd prime, so and n is a sum of two numbers a square and b square, so one of them from a square and b square must be odd. Okay. One of them must be odd and the other must be even, so that the sum becomes odd. Okay. So one of a and b must be odd, one of a square and b square must be odd, and the other one must be even. Okay. So if we take let a square is let a square be an odd and b square be even. Okay. So if a square is odd, then a must be odd as well. So we assume that a is equal to, because a is an odd number, so the general representation of odd number is 2a plus 1, okay, for some integer a, and b is equal to, because b is even, b square is even, so b must be even as well. So the general representation for an even number is 2 times some integer. So we assume that the some integer is b. So for some integer b. Okay. So now, so what will be the value of n? So n is a square plus b square. So a is 2a plus 1. So 2a plus 1 whole square, plus b is 2b. So 2b square is equal to 4a square plus 4a plus 1 plus 4b square. Okay. So we will keep all numbers with coefficients 4. So 4, and we take 4 as common from those. So we take 4 as common. So a square plus b square plus a and plus 1. Okay. So we can also write this as 1 plus 4 times a square plus b square plus a. We know that a square is an integer, b square is an integer, a is an integer. So this result, a square plus b square plus a, must be an integer. So it means n is equal to 1 plus 4 times some integers k, and this gives you the congruence n congruent to 1 modulo 4, but that is the contradiction. We have n congruent to 3 modulo 4. So that is the contradiction which contradict the fact that n is congruent to 3 modulo 4. That is it. Okay, there are two very important results related to congruence. These two results we use them, we will use them later. Okay. So the results are, so there are two results. One of them is, okay, for that let me explain first. Let a is congruent to b modulo m and c is congruent to D modulo M. So, there are two congruences, okay. So, but both are related to M, okay. So, there are two results. One of them is related to sum and the other one is the product. So, if we have A is congruent to B modulo M and C is congruent to D modulo M, then we can add two congruences. So, A plus C is congruent to B plus D modulo M, and the other one is A times C is congruent to B times D modulo M. Okay. Proof. So, it is given here that A is congruent to B modulo M and C is congruent to D modulo M. Okay. So, if A is congruent to B modulo M, then we can write as A is equal to B plus M times some integers. So, L M, and if C congruent to D modulo M, so we can write C is equal to D plus some M times some integers, yani K M. Okay. So, first equation, because first congruence gives you A plus B, A equals B plus LM, and the second congruence gives you C plus D, C equals D plus KM. So, you can just add these two equations. So, this is, you can call that 1 and 2. So, to show the first result, we add 1 and 2. So, A plus C is equal to B plus D, and we add the second terms. So, K M is common from there. So, you can write L plus K times M, and L plus K is another integer. So, you can write here as A plus C congruent to B plus D modulo M. Okay. So, because this L plus K could be replaced by any integer, for example, T. Okay. So, you can convert, or you can apply first result here to get A plus C is congruent to B plus D modulo M. Okay. The next result, okay, let me prove this in this region, the second one. Okay. Okay, for the second one, okay, for that we take AC, because we need AC congruent to BD modulo M. So, we take the difference AC minus BD, okay, that is equals to AC, and we put minus PC here and plus BC, then minus BD. Okay. So, we take C common as common from here, and we take B common from the last two terms. So, this gives you C times A minus B plus B times C minus D. Okay. Look at equations 1 and 2. So, in equation 1 we can also write A minus B is equal to Lm. So, here we have A minus B. So, this A minus B could be replaced by Lm. Okay. Then we have B. Look at equation 2, that is C equals D plus Km. So, we can also write C minus D is equal to Km, and this can be written as Km. Okay. So, we can take M as common from here. So, we will have Cl plus Bk times M. We know that this Cl plus Bk is an integer, because B, C, L, K, all of them are integers. So, the product of the sum of the product of the integer is always an integer. So, this is an integer. So, you can replace this by another integer, for example, t or x. For example, x is an integer. So, you can replace this by x, xm, and here we have AC minus BD. So, you can also write this as AC is equal to BD plus XM. Then apply first theorem here again to convert this equality into congruence. So, AC is congruent to BD modulo M. That completes the proof of the theorem. Okay, let us do an example. So, example, so 1 factorial plus 2 factorial plus 3 factorial till 100 factorial. So, this is a series, and this sum is divided by 15. Okay. This sum is divided by 15, and we have to find the remainder. Okay. We have to find the remainder. Okay. So, we know that 1 factorial plus 2 factorial plus 3 factorial, okay, plus till 100 factorial. Okay. When this result or this sum is divided by 5. Okay. So, if you look at the sum of first two numbers, okay, so the sum of first two number is 3, which is less than 15. So, look at the sum of first 3. So, this is 3 and 3 factorial is 6, 6 plus 3 is 9. Okay. Okay, let me write more numbers. 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial plus 5 factorial plus 6 factorial plus 7 factorial and so on till 100 factorial. Okay. So, the sum of first two is 3, the sum of first 3 is 9, the sum of first 4 is, so 4, what is 4 factorial? 4 factorial is 24. So we add 24 here. So 9 plus 24 is 20, 9 plus 24 is 33. Okay. So the sum of first 4 term is 33. Okay. Now, so if you consider 4 factorial, okay, so 4 factorial alone is 24. Now, look at 5 factorial, sum up to 5 factorial. So, what is 5 factorial alone? 5 factorial is 120. Okay. So, 5 factorial is 120, and if 120 is added to 133, so that gives you 153. Okay. Look at 120. Okay. 120 is divisible by 5. And what about 6 factorial? 6 factorial is 5 factorial multiplied by 6, and this 5 factorial is 120. So, 120 multiplied by 6, again 6 factorial has 120 and which is divisible by 5. So, remainder will remain 0. Okay. So, look at 7 factorial. So, 7 factorial is 5 factorial multiplied by 6 multiplied by 7, and 5 factorial is 120. So, 120. So, 120 times 6 times 7. So, again this 120 is divisible by 5, divisible by 15. So, remainder will become 0. So, it means after 5 factorial every term will have 120, okay, and every term is divisible by 120 and hence divisible by 15. So, after fourth term means fifth and onward, every term is divisible by 15. So, remainder must be 0. So, there is no need to consider the sum after fourth term, because the sum whenever this sum is divided by 15, the remainder will remain 0. So, we consider only first 4 terms. So, it means whenever 1 factorial plus 2 factorial plus 3 factorial plus till 100 factorial is divided by 15. So, the remainder will be 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial, but all the others are 0, means 0 plus 0 till 0, because you are dividing by 15. Okay, let's solve this sum. So, we have already calculated this sum. So, this sum is 33. So, modulo 15. So, this is bracket. So, because here we have 33. So, whenever 33 is divided by 15, so remainder here we will get 3. So, 3 modulo 15. So, it means the remainder is 3. Okay. After completing this example, let me recall this result that is related to two congruence. Okay, this one. Okay, let A is congruent to B modulo M and C congruent to D modulo M. So, this result is also valid. You can consider that as a corollary. So, this result is also applicable for the difference as well. So, A minus C is B minus D modulo M. So, for sum we have A plus C congruent to B plus D modulo M, and we also have A minus C congruent to B minus D modulo M. Okay. And there are some important facts as well, and you can consider them as corollaries if A is congruent to B modulo M and C is any integer, then so there are some important things. Number 1, A plus C. So, any integer can be written on both sides of the congruence. So, A plus C congruent to B plus C modulo M. Similarly, any integer can be subtracted, because it means you can take any integer, negative or positive. So, B minus C modulo M. Number 3, any integer can be multiplied on both sides of the congruence. So, AC congruent to BC modulo M, and the fourth one is A square congruent to B square modulo M, and this can be extended to A to the power n congruent to B to the power n modulo M. Okay, for any positive n. So, this is all for today. So, inshallah we will solve linear congruence equations inshallah in next class. Thank you.